when we were talking about the trig functions in chapter 4, we already, got used to this interval notation. But basically, this is how we would normally give an interval or a range of numbers in Algebra 2. And now we are going into interval notation. You've seen it's so much more efficient. So just remember that less than or equal to, right, it gets the bracket, or same with greater than or equal to gets the bracket. Okay, and so it's so much more convenient to think about. So here, if x is greater than or equal to a, right, so basically here is a, and x is greater than or equal to, so everything from a on to infinity. So we say everything from a to infinity. We close at a because it's a closed circle. And then infinity, I have no idea what infinity is, right? Can we get on a spaceship, go somewhere, get out and say, okay, I'm standing on infinity? No, we have no idea where it is. It's undefined. So it's always an open circle, okay? And then all reals is negative infinity to infinity. So why don't we do some examples here? So here is an interval. It's going from negative 2 to 12. So it starts at negative 2 and 12, and it's closed on both ends, right? So it'll be negative 2, comma 12, and brackets on both ends. We always go smallest to biggest in increasing order of numbers, right? Okay, so B, x is greater than negative 17. So starts at negative 17 and goes to infinity, right? And that's how I write it. Starts at negative 17, goes to infinity. You see how much more convenient it is to think about? And these are open on both ends. Okay, so take a look at here. X is less than 3 or greater than or equal to 8. So now I have two. One is negative infinity to 3, union 8 to infinity, but we close the 8. U is, this means union, meaning like this or that. It's a symbol that we learned in like number 3 before. So basically it means like that and that. Yes.
Do you always go from the smaller number to the
yes.
number? Okay.
So we would never say 3 to negative infinity. Students always want to do this, right? 3 to negative infinity. We don't. That's not conventional. We don't like that. Okay. 3 to negative infinity. Okay. So x is less than 0. How would I write that?
Negative infinity comma 0.
Negative infinity to 0. Okay. Questions? Yeah. Yes, right. It's or, so we write it here. So basically it's this and then that region. Okay, so a function, right? What is a function? Basically a function is a relation that if you have your domain set in, input or domain, and then if you have your range, so basically each element in the domain has exactly one element in the range, right? So let's think about that for a minute. If domain is the x values, right, here, then each x value only has one corresponding y value. So if x is 1, there is only one corresponding y value. If x is negative 2, there is only one corresponding y value, right? So what did we normally do to test that? Vertical line test, right? So how does that look? A function is a set of ordered pairs in which no two different pairs have the same x value. So for example, if I have 1 comma 3, I can't also have 1 comma negative 2. For one x value, I can't have 2 y values, right? So the way we test for a function is the vertical line test. And the way that works is, if you have a graph of a relation or of a function, if you draw a series of vertical lines, each vertical line is only allowed to cross the function once, okay? All right, so let's see whether each of these is a function. Take a look at the first one. Is that a function?
Yeah.
Right, none of the x's repeat, so yes, it's a function. What about here? No, because x's repeat with different y's, so no. What about here? Yes, that's a function. What about here? No. Right. Okay, so for each x, you would have 2 different y's. Okay, so this is a no. Yes.
Is it because it's 2y squared and y squared?
Right, so suppose x was equal to 1, right? We picked an x value, right? So when you plug it in there, how much is y? Right, when you take a square root, y is plus or minus 1/2. So when x is 1, you have 2 y values. Right, x equals 1, you have 2 y values, so that means it's not a function.
But let's say it wasn't y squared, then would it be?
Right.
Okay.
Okay, function notation. So in function notation, instead of saying y, we use the symbol f of x, right? And it's the same exact thing as y. So now, it doesn't have to be f of x though, right? It could be h of x, it could be g of x, and it doesn't have to be x. It could be v of t, it could be s of t, it could be whatever you want, right? Basically, here's what this represents. So suppose you use f of x to represent y, then x is representative of the values in the domain, right? X is the domain. And then y, that dependent variable, is the range, right? And it's called the dependent variable. So then x is the independent variable, right? So you always have in this notation the independent and the dependent variable. So for example, in the case of s of t here, t is the independent variable and s is the dependent variable, right? So what do those two terms mean? Dependent and independent. Yeah. So basically the independent variable is just changing just because, right? But based on how the independent variable changes, that changes the outcome, like you said, of the dependent variable, right? So it could be t and velocity. It could be, you know, whichever you want. Okay. For each, we've done something similar to this before, right? And now we're going to do it again. So we're going to find f of a plus h minus f of a over h. Why? Because this is very important in what we do in calculus. Yeah.
Should that not be for a? Should that not be f of a equals a squared minus 2a?
No.
There's no f of x.
Right, there is though. Hang on. Okay, look. So, do you remember? Recall. In chapter 4. We were given like a function like sine of x or something, and then we had to find f of x plus h minus f of x over h. Do you remember that? Okay. Now I'm given f of x equals this. This is what I'm given. I'm given f of x. What I need is f of a. Okay? So f of a is going to be I'll write it here. F of a is going to be f of a plus h minus f of a over h. So now, let's see what this is going to look like. I'll color code. F of a plus h, right? Where is my f of x? This. So now, what's f of a plus h? What do I do? Let's do that here. What's f of a plus h? That means for everywhere I see an x, I'm going to put in a plus h. Does that make sense? This is f of x. I'm given f of x. Now, if I were to look for f of 2, what would I do? Put 2 into wherever I see an x, right? Now, what if I needed f of a? I put an a in there, right? What if I needed a f of a plus h? Then I put my a plus h. So f of a plus h was going to be a plus h squared minus 2a plus h. Okay? So look, the skeleton of this, when I zoom out, I have x squared minus 2x. X squared minus 2x. Now, minus, I'm going to continue. I need f of a. What was f of a? A squared minus 2a. Notice the parentheses all over h. Okay? So now let's simplify that. The green part, first it'll be a squared plus 2ah plus h squared minus 2a minus 2h. And then the blue part, minus a squared plus 2a, all over h. You'll appreciate this next year in calculus. Ooh, I'm running out of space. Okay, the most beautiful thing happens now. Lots of things cancel. A squared and a squared. What else? Negative 2a and positive 2a. So what am I left with? 2ah plus h squared minus 2h over h. You can factor out a 2, but look, you have an h in the denominator. Does an h appear in every single term of the numerator? Yes. How many h's on the bottom? 1. You can cancel out 1h from every single term of the numerator. 1, 1, 1, 1. You couldn't do this if one of the terms didn't have an h. So finally, this is 2a plus h minus 2. Okay? That's it. Right, I mean f of a equals, obviously that's what f of a was, right? Okay, so that's it for this. Okay, so for f of x equals 3, what does that look like? What does the graph of that look like? It's a horizontal line at x equals 3, right? So now, what's f of 2? 3. What's f of 4?
3.
What's f of negative 250?
3.
3, right? So okay, so suppose we want to find f of a plus h minus f of a all over h. What's f of a plus h?
3.
3. What's f of a?
3.
3. So that is 3 minus 3 over h. 0. Okay? What we found here that you don't know about, right? It's a secret now, is the rate of change of a function. Like, what's another word for rate of change? slope, right? Does it make sense then that the slope here would be 0? Because how much change is there here? 0. And this is the beginning of rate of change, and then we're going to take this with us, and then in chapter 12, when we do some preliminary calculus stuff, you'll see that it all comes together, okay? All right, so a function with an unspecified domain is called the implied domain, which is the set of real numbers, okay, where the function is real. Okay, so if I just give you a function, that implies that that exists on the domain where everything is real, okay? So how do we find the domain? Rather than saying all the points where the function exists, because that could be like infinitely many, we just say where it doesn't exist. So we just exclude, right, the points where it doesn't exist. Where would a function not exist, you say? Well, it's when there is division by 0, right? Or if you took the even root of a negative number, right? These are two huge no-nos, right? You can't divide by 0, right? So I have like a whole series of math t-shirts. My next one is going to be one that says everything is fine until you divide by 0, right? Because you can't divide by 0. My kids know that. My little kids know that. You just can't divide by 0. The world just blows up, right? And then also, when you take a root of a negative number, okay, it's imaginary, but it's still not real, okay? So these are two examples that have points where the function is not a real number. One, you see here, you're dividing by a potentially 0, by a value that's potentially 0, right? So here, when x is what, will this denominator be 0? Negative 2. So here, x cannot be negative 2. That means, okay, here is negative 2. X can't exist there. But you know what? It's all good here, and it's all good here. So its domain will be from negative infinity to negative 2 here, and from negative 2 to infinity. Okay? What about this one? This is good. So what does this look like? Is it okay to have a 2 for x? What? Yeah, because then you get root 0, which is 0, and that's fine. Is it okay to have anything less than 2? Greater than 2?
Yes.
Yes, you could have greater than 2. So the domain here, so this is what you can't have, but everything here is cool, right? So the domain here is 2 to infinity. Okay? All right. Now, we're going to break, in order to find domain and range, right? We're not going to use our graphing calculators to find domain and range, right? In order to find domain and range, there are some tips though. First of all, we can classify functions into 3 dominant categories. One is polynomial functions. You should all know what polynomial functions are, but I'll tell you. A polynomial function is one where the variables, like x, have exponents which are 0 or positive integers. So x to the 0, x to the 1, x to the 2, x to the 3, right? Those are polynomial functions. So an example is f of x is equal to 3x to the 4 minus 2x cubed plus 3x, and so on. Okay, you just know that the polynomial function always has a domain of all real numbers. Okay, so take a look at this. Is this a polynomial function, A? Yeah, so the domain is all real numbers. Is this a polynomial function? Yeah, so the domain is all real numbers. Think about it another way. Is there a value of x that when I plug it into this function, it'll give me an imaginary number? No. Is there a value of x that I cannot plug into these numbers? No. Everything works. That's how you know. Okay? Next is rational functions. all the exponents are are integers or zero, positive integers or zero. So x to the 2, x to the 1, x to the 0 here. Okay? All right, next we have rational functions. This is where you have variables in the denominator. Okay? Basically, what is the domain? The domain is all of the numbers except for the ones where the denominator will be 0. Okay? So, what you do is check to see where denominator is 0. Guess what you do first? Yes. Okay? All right, so here, look at this one. This is n of x. So unconventional, but still pretty cool. Okay? So basically, when we factor this, we get 2 over x plus 4, x minus 3. So the condition is x plus 4, x minus 3, the denominator, should not equal to 0. Okay? So, x should not equal negative 4. X should not equal 3. So we're not going to do it in this detail every single time. But basically at negative 4 and negative 3, this function can't exist. But can it exist anywhere else?
Yes.
Yeah. So the domain is negative infinity to negative 4, negative 4 to 3, 3 to infinity. Right? So imagine writing like y, like x is less than negative 4, and then negative 4 less than x less than 4. Like there's so much unnecessary notation. Okay? All right, take a look here. This should not equal 0. Okay? So what is t not allowed to equal? 1 or negative 1. So t can't equal plus or minus 1. So my domain is negative infinity to negative 1. And then what?
Negative 1 to 1.
Negative 1 to 1?
1 to infinity.
1 to infinity. That's my domain. Okay?
Is the u and u as
The u is set notation, right? So it's basically like the union of these two. Okay. It's the union of this range and that range. It's the marriage of all those. Okay. So look at this one. Here you have two separate fractions. Well, you know what? If you were to do a common denominator, what would the common denominator have been? X plus 8, x minus 10. So that would be like I don't care what the numerator is. That would be the denominator in total later, right? So here, what can x not equal? Negative 8 and 10. So the domain is negative infinity to negative 8. Oh my. And here's where you shouldn't write infinity and 8 in the same line, right? Because I always like transpose them. And then negative 8. See? Negative 8 to 10, and then 10 to infinity. So now, would you have to write down x can equal negative 8, x can equal 10? Not really. If you could go from here straight to the answer, that's fine. You know what? We really do have bigger fish to fry here. Setting this equal to 0 and factoring this is an algebra 1 skill. So, you know, I won't even give you partial credit for wanting to do that. I mean, you just give me the right answer. Okay? Okay, so x squared plus 1. Huh? That one's what? Henry, say it. Is there any way to plug in an x and get a negative number?
No.
Because check it out. If you plug in a positive number, you're already okay, right? If you plug in a negative number, this is going to square it and then add 1 to it, right? So it's still going to be greater than 1, greater than 0, okay? So the domain here is all real numbers, okay? no values for which x squared plus 1 equals 0. So we talked about polynomials, we talked about rational functions. Let's talk about radical functions. And that's not a political statement. Okay? The domain. Okay, so radical functions we have to classify into two as well, right? You can get an even nth root, so fourth root of something, square root of something. What's the deal if you have an even root?
You can't get it inside the terms to be equal to 0.
Right. The inside must always be positive, right? So for these, the radicand, the inside, is greater than or equal to 0, okay? Say that word at your next math party and see how popular you will be, right? Go in there talking about radicands. Okay, so what if you have an odd root? So like a cube root or a fifth root. Can you get a negative number in here? Well, so what's the cube root of negative 8? It's negative 2, right? Not 2 root 2, negative 2. So you could totally get a negative or a positive number in here. That means the domain of an odd nth root is all real numbers. Okay, so we only have to worry if it's an even root. Yeah.
When you have a negative inside the square root, when you have like a odd number on the square root, could it be positive and negative?
Sure. Positive and negative. Okay. So take a look at this one, even root. Okay, so what's the condition? 7x minus 70 has to be greater than or equal to 0. Can it be 0? Yeah, it could be 0. The stuff inside the root can be 0, right? So 7x has to be greater than or equal to 70. X has to be greater than or equal to 10. That means my domain is 10 to infinity. Okay. Same thing here. So x minus 5, x plus 3 has to be greater than or equal to 0. Right? And here is where we have to think a little bit. Yes?
Why do you have one bracket on the number?
The 10 to infinity?
Yeah.
Remember, infinity never gets a bracket because we never know where infinity is. Because x can equal 10. When x is 10, you get 0 in the...
Oh.
Okay, so here, okay, the first one was linear. This is non-linear. Remember how to do non-linear inequalities? You have to do a number line. On the number line, you put the 2 points that you got from here, right? Now you have 3 regions. Is that right? Yeah? So now what do? Right, so basically you have to pick a number from each region, plug it in here, and see if you're going to get a positive or a negative value. So here's how I do it. A number from here, like negative 5, right? If I plug it in the first parenthesis, does that give me negative or positive? What about the second one? Negative. Negative times negative, that'll be positive. Okay? If I plug in a 0 into the first parenthesis, I get negative, positive, that's negative. If I plug in a number from here, like 10, into here, I get positive, positive, positive. Okay. So what is the region which I want? I want all the positives. So I want this region and that region. So the domain will be negative infinity to negative 3, 5 to infinity. Yeah. I always go in here. That's the easiest thing, right? Because then I have like one parenthesis, one parenthesis. So look, so if I plug in a 0 here, I get negative. If I plug in a 0 here, positive. Negative times positive is negative. Okay?
And so the negative 4.
Right, you get negative, negative, positive. Okay, here we go. Cube root of x minus 4. What do we think about the domain? All real numbers. Ooh, what about that one? What does that look like? That's the square root of 9x minus 2 cubed. Is that right?
Is it not like the square root of 9x minus 2 and then in parentheses?
Same thing. It's the same. You could put the cubed underneath or outside. Okay, so now, what does this mean? The stuff inside has to be greater than or equal to 0. Huh? No, because even if you had put the cube, you could just take a cube root of both sides and it goes away. Okay? So then x has to be greater than or equal to 2 over 9. So my domain is 2 over 9 to infinity. Closed or open on 2 over 9? Closed. Okay, now we're getting to my favorite ones. What's the deal with E here? E's got all sorts of issues. What does E have? What type of function is E?
It's a rational radical.
It's not only a rational function, it's a radical function at that. So, okay, so let's focus on the radical function. The radicand must be greater than or equal to 0. Okay, fine, if it was a radical on its own. But what does the rational function add to it?
Equal 0.
It can't be 0. That means so that means what value can the radicand have? Can it be positive inside here?
Yeah.
Can it be 0 inside there?
Yeah.
No, it cannot be 0. So that means x plus 2 has to be greater than 0, not greater than or equal to. Okay, strictly greater than 0 is how we say that. So x is greater than negative 2. That means the domain is negative 2 to infinity. So do you see how there is not a clear-cut formula that each case you take on its own, right? Okay, what about this next one? Oh my, this next one. Oh, this next one. Okay, what does the radicand, yeah. The denominator should not equal 0. Okay, so take a look at this one. This, right? What are the conditions here? X minus 3 has to be greater than or equal to 0. That means x has to be greater than or equal to 3, right? Can it be 3 for that root? Yeah. Okay. What does this denominator tell us? It just can't be 6, right? The denominator says x can't be 6. Okay, so let's think about this. On the one hand, it's telling us that it has to be 3 or above. On the other hand, it's telling us that it cannot be 6. So, for heaven's sake, what can this be?
3 to 6.
It could be those numbers, and it could be all those numbers. So the domain is 3 to 6. Can it be 3?
Yeah.
Can it be 6? And then 6 to infinity. Isn't that cool? All right, those are my favorite types of problems. Okay? Okay.
I like the ones that are like what is 1 plus 1 equals 1.
Uh-huh.
Let's go.
What are these? Okay, I'll give you 2 minutes to do the domain for G and H, starting now. I'll stop this for 2 minutes. Right, it can equal 0 on the bottom, so H is, you know, just 3 over 2 to infinity. Okay.
For G,
Uh-huh.
isn't it like negative when you plug it? Like, are you supposed to do this when you plug it into?
No, that was when we had a radical and we wanted to test it to see where it was positive, right? When we had a radical here for B. This one, you just have to look for values where the denominator will be 0, right? Okay, let's move on to piecewise functions. Okay, so here, there is okay, so here's how piecewise functions work. Your f of x, your function is split into 2, and the graphing region, right, the xy coordinate plane is divided into 2 domains, into 2 regions. So basically, the way the function is written is here you're given what to graph, and here you're given where to graph. So if you see, you've got 2 functions. One is graphed where? In the region where x is less than 0, so on the left side of 0. And then you've got another one that's graphed in the region where x is greater than or equal to 0. Okay? So just to take a look, on the left side here, what kind of function is it that we have to graph?
Linear.
It's a linear function, it's a line. On the opposite side, it's x squared quadratic, so it's going to be a parabola. Okay? So what I do first, okay, for each function, plot point on boundary. So for the first one, the boundary here is x is 0. Now normally we would say, okay, you know, like let's have like a dotted line, you know, as the boundary, and then in pre-calc, I want to take away those crutches as much as I can. So when x is 0, what's the value of the function on top? 2, right? When x is 0, y is 2. X is 0, y is 2. Now, here it's open. It's an open circle. So at x is 0, y is 2, I put an open circle. Okay? When x is 0, what's the bottom function? How much is the bottom function?
2.
Also 2, right? Okay, so now let's just stay with the top function. This is a line. So now you just have to graph that line somehow, right? And you've got all of these tools under your belt right now to graph a linear function. What's one thing you could do to graph that linear function? Rise over run, but you have to go the opposite way, right? Because you're only graphing here. So if this is negative x, you know it's going down. So if you're going to do rise over run, if you're going to do slope, if you go up 1, or if you go down 1 to the right 1, you go in the opposite direction. So you have to make sure to go opposite. What's another thing you could do? Can you just see what the value is at like negative 2 and plot it? How much is it at negative 2? At negative 2? It's 4. So that's what this looks like here. Okay. This one here, when x is 0, y is 2, except, so it's the same point, except this is a closed circle. When you have open and closed overlapping, you just close it. Okay? And here we're graphing a parabola. How do we graph a parabola? If you go to the right one, you go up 2. Is that right? Right one up 1, and then right 2 up 4. Okay. Oh, and that's it. Okay, I'm going to stop here. Tomorrow I'm going to do the rest of this section and also section 2. For homework, I want you to start doing this. You could do a lot of the ones in the beginning, right? So start doing that because then you're going to have double homework. So I would suggest you start doing this now.